Okay, so this is the sixth lecture on advanced course in classical logic. Today we study games, Ehrenfeucht games. So this is the first lecture of the second part. So we had the first part on classical propositional logic. And now we came to the second part of our course, classical predicate logic, or classical first order logic, another name. So we only briefly recall what is the classical predicate logic or first order predicate logic. Because this logic is studied in the standard course, many theorems are proved in the standard course. So we know many properties of this logic. But only briefly, what are the syntax and the semantics of this logic? So we again have connectives, negation, conjunction, disjunction, implication. What is new? We have quantifiers for all and exist. The universal quantifier, the existential quantifier. We will also have variables, but now we call them individual variables. In the propositional logic, we had variables, but they were propositional variables. They were variables for propositions. They denote propositions, statements. Here, variables denote some elements of a set. Tables, people, cars, numbers, matrices, whatever. In our language, we also have predicate symbols. We will denote like this. So in general, this is a long notation for them. N indicates how many arguments does this symbol have. So this is the n-ary predicate symbol. It requires n arguments. And I is an index ranges over a finite or infinite set. So we will have either finitely many symbols or countably many. And today we will even have only finitely many. Games are applicable to finite vocabularies, to finite sets of symbols. In general, the first order language also has functional symbols. They are denoted similarly, but you have F instead of P. So these are notations for predicates, for properties, for n-ary properties. These functional symbols are notations for functions. Functions with one argument, functions with two arguments, and so on. And also usual first order languages also have constants, finitely many or countably many constants, CI. But today in our lecture, we will only consider languages that have predicate symbols only. They don't have functional and constant symbols. And we will have only finitely many predicate symbols. This will be essential. So in general, a signature is a triple that has a set of predicate symbols, a set of functional symbols, and a set of constants. So in today's lecture, the second and the third component are empty. For example, our signature may have three symbols. P is a ternary symbol, Q a unary symbol, R a binary symbol. They are all relational symbols or predicate symbols, you can say predicate symbols or relational symbols. So in particular, we can write formulas like this. In the standard course, what goes next is the definition of the formulas. First of terms and then of formulas. Today we will not have terms as additional set, because in our case, in our lecture, terms are just variables. So forget about terms for today's lecture. But the definition of formulas is usually given by induction. I will not give the exact definition of this set of the formulas. I will only give some examples. So, for example, this is a formula. You can write a predicate symbol. In parentheses, you write its arguments. Its arguments can be any variables. They may be the same, they may be different. It doesn't matter. You can combine these formulas using conjunction, disjunction, negation, implication. So this is a formula. You can use quantifiers. You can write exists y for all x here. So for all x, its scope is only this formula p x y x. And exists y, its scope is this whole part. So y, this y and this y are under this quantifier. If some variable is under the quantifier, it is called a bound variable. If it is not under quantifier, it is a free variable. This x is not under any quantifier over x. So it is a free variable. And all other variables are bound variables. In particular, this x is a bound variable. It is under this quantifier for all x. This y is a bound variable. This z is a bound variable. And this is a free variable. We can build another formula like this, and then this x becomes a bound variable. And so this formula doesn't have free variables at all. If a formula does not have free variables, it is called a sentence or a closed formula. So I hope you remember how to write formulas, and in particular closed formulas of some signature. In our case, this is a signature with 3 symbols. Formulas that are closed, that are sentences, denote, in some sense, a statement that is either true or false. It denotes either yes or no. Statements about what? About some model. So in order to give a model or an interpretation of this signature sigma, we need 2 things. First, we need some non-empty set D. It is called a domain. And we need to every symbol from sigma, to every predicate symbol. In our lecture today, we consider only predicate symbols. To every predicate symbol, we assign its meaning in this model. What is the meaning of the symbol P? So assume that P is a predicate symbol, n-ary predicate symbol, it has n arguments. Then its meaning, P star, is an n-ary predicate, n-ary property, in other words. So it is a subset of D times D times D, and so n components. So an n-ary property of with n arguments. So we usually have unary predicates, binary relations, and so on. And so in general, they are n-ary relations. Now, so this is a model, a set, and predicates for each symbol from our vocabulary or signature. Now, if we have a closed formula, then, as I said, it says some statement about a model. Formally, this is defined as follows. We define the following notion. A formula is true in a model. It is denoted by this. So in the model M, the formula A is true if we assume that A is a closed formula. This, of course, this definition is defined by induction, is given by induction. But if we use induction, so we decompose this formula A into smaller components, we obtain a not closed formula, a formula with free variables. So we need a more general notion in order to formulate this definition. We need a more general notion. A formula with some variables, free variables, x1, xn, and so on, is true in the model M if we assign some values to the variables x1, xn. So this is quite a long definition. It was given in the standard course. Today, I will assume that we understand formulas intuitively. So let us just give examples. So consider this simple model. D is the set of natural numbers. And we have only one binary predicate, less than. So can you say, is this formula, this is a closed formula, is it true in this model or not?
Well, it's true, because for each element there really exists the next one, which is bigger.
Yes, for example, we can take y equals x plus 1, and so this formula is indeed true. Yes, it expresses the property that this set is not bounded from above. It doesn't have a maximal element. Another sentence, closed formula. Is this formula true in this model?
No, because there is a 0, which is the last one.
The first, the first. So this set has a minimal element, and the minimal element does not have a smaller element. So we say that in this model, this formula is not true. Is this formula true? There exists y less than x.
Well, x there is a free variable, so I think we have to close this formula by applying this quantifier for all x, and thus it is, well, like this sentence B. Then no.
The thing is that we ask exactly, is this formula true? We don't apply quantifiers to x. Exist x or for all x. So it is not enough. There is no. We don't have enough information for saying, is this formula true or not? And for this reason, we can't define this notion only for closed formulas by induction, because when we decompose, when we remove quantifiers, we obtain formulas like this with free variables. And what shall we do? We need an assignment. For example, we can say that in this model M, this formula C is true. C of 7 is true, because if x is 7, then of course there is y, which is smaller. In this model, this formula C is not true for 0. So M, we write M doesn't model C and then 0 in square brackets, because 0 is the smallest element, it doesn't have a smaller. So in order to say, is this formula true or not, we need some additional information, an assignment to every free variable, some element of our domain. But today we will consider only sentences, only closed formulas. So for a closed formula is some statement. It is either true or false. Now, consider the following situation. We have two models, D and M and N. We say that they are elementary equivalent if the same sentences of our signature are true in them. So for every sentence, it is true in M if and only if it is true in N. And recall that we also have the notion of isomorphism. Two models are isomorphic if there is an isomorphism. Isomorphism is a bijection from one set to another set, such that for any two elements from the first set, and for any predicate symbol, so here I gave an example for a binary predicate R, but in general we have in our signature sigma many predicates with many arguments. So for example, for a binary predicate, it is true for this particular pair AB in the first model if and only if this predicate, its meaning in the second model, is true for its image, for the image of this pair. And the same should be written for every predicate symbol in our signature. So you can recognize the notion of a isomorphism of linear orders or partial orders and so on. It is almost obvious, simple proof, says that if two models are isomorphic, then they satisfy exactly the same sentences. The same sentences are true, so they are elementary equivalent. But the converse doesn't hold in general, and we will have some examples. So it is quite obvious that natural numbers and integer numbers are not isomorphic as linearly ordered sets. Why?
Because of the minimal element.
Yes. So if we have an isomorphism, then it must preserve the minimal element. But N has the minimal element, Z doesn't have the minimal element. So they are not isomorphic. But then the natural question is, can we distinguish these two models by some first order formula? So in fact, we can distinguish. So there is a first order closed formula. So there is a closed form. All formulas today are first order, so I will not say first order. There is a closed formula, a sentence, that is true in one model and false in another model. Can you write this formula?
I think yes. It's, well, about minimal element. Something like exists X that for all Y or Y is bigger than X or equal.
Even without equal. Here I wrote a negation. So you said exist X for all Y. Y is less than X. And so this formula, every element has a smaller element. It is true in Z, but it is not true in M. Because if we take X to be 0, it doesn't have a smaller element. Today we will even see that this is the smallest formula in the sense that we need two quantifiers. We cannot distinguish these two models by simply one quantifier. Moreover, we cannot distinguish these two formulas by a formula with many quantifiers, but in which every quantifier is at level 1. So in this formula, this quantifier is at level 2. So this is level 1, this is the first quantifier. Then inside the first quantifier, there is another quantifier. So we have depth 2. This formula has depth 2. It has quantifiers inside quantifiers. And today we will see that we cannot distinguish these two formulas by any formula, any long formula in which quantifiers are of depth 1 only. So we need depth too of quantifiers. Okay, so this is a simple example. The following may be less trivial. Let us recall what is z plus z. So we have two linear sets, z minus z less than, z less than. For any two linear orders, we can take their sum, their disjoint union, and order them like so we have a first component like z and the second component that is isomorphic to z. So let me show this on the picture. And we can even draw on this picture. So here below we have z plus z. Can you see this picture?
Yes.
Yes.
Yes. So, here we have just integers ordered by this less than relation. Here we have some set that is ordered like z. I denote it by z prime. And here we have another set ordered again by sz. So we have two linearly ordered sets. Are they isomorphic? Do we have a bijection that preserves our relation less? Of course, there is a bijection between the first and the second set, because this set is countable and this set is countable. So there is a bijection. So the question is, does there exist a bijection that preserves the order?
Well, no, because in the first set it's just regular z. For each two elements, there is a finite number of elements between these two elements. And for lower model, there is two elements, for example, 0 of z prime and 0 of z prime prime. And there are infinitely many elements between them.
And we also need some statement like any bijection, any isomorphism preserves this property that between two elements there are finitely many elements, or between two elements there are infinitely many. So this property is preserved. So yes, so we can say the following. We have take this element here and take this element here, which corresponds to 0. But in fact, we can take any element here and any element here. Any element here. Here we have A. So assume that there is a bijection that preserves order. Then this element goes to some element here. So A prime. This element goes to some element here. So this is B prime. And now what can we say? Where is the contradiction? And there is only finitely many elements here, but infinitely many elements here. So a bijection cannot map infinitely many elements to finitely many elements. So this is a contradiction. So there is no bijection. So these two ordered sets are not isomorphic. The question is, do they satisfy the same sentences? So in our proof, we use the following notion. There is infinitely many elements between these two. We cannot simply write this property in the first order language. We need to write there exists x1, x2, x3, and so on. We need an infinitely long formula, but we can't write infinitely long formulas. So the question is, do these two structures satisfy the same sentences? What is your guess? Yes or no? You can see, for example, that some properties are the same. Less than is irreflexive here, and it is irreflexive here. So for all x, no, it is not x less than x. It is true in here and here. Less than is transitive. It is true here and here. It doesn't have maximal element. It is true here and here. It doesn't have minimal element. You can even write more difficult sentences. For example, for any element, there is the next bigger element. So there is an element. For any A, there is B, such that B is bigger than A, and there is no elements between A and B. You can write this formula. You can easily write, and it is true here and here. So again, we could not distinguish. So the question is, do we have any formula that distinguishes them? And in fact, there is no such formula. So the laws of these two structures are the same if we write laws in the first order language. So they are not isomorphic, but the laws are the same. And games are the tool that will enable us to prove this, that that satisfy the same sentences. Okay, so what are games? Let us go to the games, to the main part of our lecture. So we will have two structures, possibly infinite structures like in our examples. So they are fixed. The players will play on these two fixed structures. There are different names for these players, either player 1 or player 2, novator and conservator, spoiler, тот, кто портит, да, дубликатор, тот, кто, как сказать, имитирует, повторяет шаги первого, можно так сказать. Значит, еще люди, так сказать, более экстравагантно так обозначают. Два игрока, один for all, другой exist, потому что вот как бы их роль будет как раз вот похожа. Один разбирает кванторы для любого, другой кванторы существует как бы. Вот из доказательства видно, на самом деле, почему именно к таким кванторам. Более того, совсем уж романтические авторы пишут Абеляр и Элоиза, а романтические экстравагантные даже пишут вот так. Вопрос, кто-нибудь знает, кто такие Абеляр и Элоиза из слушателей?
Судя по всему, нет.
Диана, может быть, знаете?
Нет, не слышала.
Вообще, философия, кстати, была уже, да, у вас? Ну, или, не знаю. Ну, это там никак... Ой, пропал звук немножко. Сейчас что?
Сейчас философия у нас идет.
Идет, да. Ну, вот как бы будете, возможно, касаться его, ну, хотя, зависит от автора, конечно. Да. Так, ну, ладно. Ну, Абеляр такой философ был, там, кажется, 13-14 век. Там, например, у нее есть книга «Да и нет», где он там изучал, описал около 400 противоречий Библии, в общем, богослов, философ и так далее. Ну, а Элоиз, соответственно, его возлюбленные. Там есть целая история. Вот можно посмотреть, вот этот хороший фильм есть про это дело. Значит, мы будем часто обозначать вот так. Первого игрока P не эквивалентно, второй эквивалентно. Ну, произносить это сложнее, поэтому будем говорить игрок 1, игрок 2. Но вот как бы вот это обозначение как бы напоминает, сразу подсказывает, за что борются два игрока. Кто что хочет доказать друг другому. Значит, тут такой короткий экскурс в русский язык. Да? Значит, игрок первый, он на самом деле будет пытаться доказать, что эти структуры не эквивалентны. Он найдет какие-то там вот свидетельства. В качестве свидетельства будут какие-то элементы на самом деле, что они не эквивалентны, что они различаются формулой. А второй будет пытаться доказать, что нет. Те элементы, которые первый пытался найти, им соответствуют и вторые, которые никак не отличаются по сути от первых. По сути, ну вот по нашему языку. Но, конечно, это очень условные такие фразы. So the aim of the first player is to show that these two models are not elementary equivalent. And the aim of the second player is to show that they are elementary equivalent. Hence, we will sometimes use this notation for the player 1 and player 2. But I will call them player 1 and player 2. It is simpler to pronounce. So what is the game? How this game is played? At the very beginning, round 0, the player 1 chooses some natural number. 1, 2, 3, and so on, starting from 1. And after this, the players will play n rounds of the game. At every round, the following happens. The first player takes some element either from the model M or from the model N. So he has a choice from which model to take the element. So he chooses either M or N, and if M is chosen, then he takes some element from M or some element from N. The second player replies. His move is the following. He takes the element from the opposite model. So if the first model was M, then the second takes the element from N, and vice versa. So at the first round, the two players take some elements A1, B1. It doesn't matter who of them takes from M, who from N. At the second round, A2, B2, and so on. So after n rounds, we will have n elements from the first model and n elements from the second model. At this stage, we don't need the information who of the players takes the element from M and who takes the element from N. Notice that at every round, the player 1 has the choice, either an element from M or from N. Now we have n elements here and n elements here. We need to compare them. So the game stops, and we need to decide who wins in this particular game. But we have in our language some predicate symbols, unary predicate symbols, binary predicate symbols. By the way, these games are defined for finite signatures. So we have finitely many predicate symbols. And now we try to find the following. Can we distinguish these two tuples of elements by any predicate symbol? What does it mean? For example, we take some symbol P7. For example, it is a ternary predicate symbol. It takes 3 arguments. And then we apply it in all possible ways to elements from the first model, to these elements A1 and from the first model. And similarly, we apply it to the elements of the second model. And we need to check if in the first element we obtain true and the second we obtain false, then the first player wins. If in all cases we obtain the same answer, either true true or false false, then the second player wins. The second player wins this particular game. Итак, вот есть еще такое понятие партия, да, вот как в шахматах там, или в любой другой игре. То есть вот мы проигрываем конкретную партию, этот выбирает элемент, этот выбирает элемент, этот выбирает это. Да, ну на первом шаге выбирается длина, сколько времени будут играть. Выбирается первым, причем игроком. Потом вот они выбрали по n элементов, и дальше примеряем к этим n элементам всевозможные предикатные символы, причем всевозможными способами. Да? На первое место можно ставить любой элемент из A1 на n, на второй любой элемент из A1 на n и так далее. Но если мы поставили вот такие элементы с такими номерами, 3, 5, ну скажем 3 вот здесь, то и из второго вот этого набора тоже надо подставлять именно те же самые вот элементы, с теми же самыми номерами. И смотреть, у нас всегда здесь и здесь не отличались. Да, вот сколько способов вот здесь вот, сколько тут проверок потребуется, вот когда если предикат трехместный, скажите. Если предикат трехместный, и мы выбрали по n элементов слева и по элементам справа, сколько вот таких проверок потребуется сделать?
N куб.
N куб, конечно, да. Можно на места ставить и одинаковые элементы, нет, это не запрещается. И в том порядке, и в другом порядке, да. А3, А5, и опять А3. Да, значит, вот... Но ограничение, что у нас конечная сигнатура, не в том, что тут вот алгоритмически что-то проверить можно будет за n куб, а в том, что для бесконечной сигнатуры само утверждение, в принципе, не будет верно. Утверждение, которое еще не сформулировано. И вот в этой конкретной партии, если мы смогли каким-нибудь предикатным символом на каком-нибудь наборе отличить, ну, то есть тут на наборе оно истина, а тут на наборе, вот на соответствующем наборе, да, вот эти буквы, элементы соответствуют друг другу, как бы они выбрались. Если смогли отличить, то выиграл тот, кто боролся за отличение, то есть первый игрок. Если не смогли, то второй. То есть, в принципе, вот это все можно, конечно, делать и для бесконечных сигнатур. Вот эта игра осмысленна. Другое дело, что она не будет связана той теоремой, которую мы сейчас сформулируем, с неразличимостью этих моделей формулами языка. Она будет связана, но некоторыми другими формулами другого совсем языка. Значит, в теории игр есть такое понятие выигрышная стратегия. Winning strategy. Ну, кто-то может объяснить, что это такое? Это фундаментальное понятие из теории игр. Я здесь его не буду приводить, так сказать, его долго формулировать, что такое позиции, что такое там допустимый ход и так далее. Вот кто-то на пальцах может объяснить, что такое выигрышная стратегия? Наверняка у всех есть такое понятие, как бы уже все играли в шахматы.
Ну, интуитивно это понимается как какой-то алгоритм, возможно, довольно сложный, который учитывает поведение как свое собственное, так и другого игрока, который обязательно приведет к выигрышу.
Такой способ играть, да, способ делать ходы на каждом шаге, такой, что как бы ни ходил другой игрок, непременно в конце будет выигрыш, win. Единственное, только поправлю, слово алгоритм здесь ни при чем, потому что если у нас там две структуры, одна мощность континуум, другая гиперконтинуум, то ни о каком алгоритме речи быть не может. Просто это некоторый способ. А что такое способ? Это, ну, фактически это функция, которая выражает текущую позицию, вот как уже к данному моменту они сходили, в то, куда, собственно, ходить. Ну, в данном случае там две вещи надо сказать. В какой из моделей ходить и в какой именно элемент той модели ходить. То есть это функция, она вовсе не обязана быть каким-то алгоритмом, и вообще, надо сказать, если там из континуального множества в континуальное, то тут вообще слово алгоритм неприменимо в принципе. Значит, понятие выигрышной стратегии. Способ так играть игроку, что как бы ни играл противник, что бы он ни делал, все равно будет выигрыш от игрока. Общая теория игр про вот эту конкретную игру доказывает, ну, это, собственно, несложно, это видно так, что либо у первого игрока есть выигрышная стратегия вот в этой игре, либо у второго есть выигрышная стратегия. Значит, тут все партии оканчиваются либо выигрышем одного, либо выигрышем другого, за конечное число шагов, причем ничьих никаких нет. Поэтому общая теория игр, надо открывать учебники по теории игр, и она гласит, что тут либо у первого есть выигрышная стратегия, либо у второго есть выигрышная стратегия. И вот у кого именно, и как это связано с моделями МН, с тем, какие формулы были верны. Вот то, как связано, это как раз тема наша. А что такое выигрышная стратегия и почему ровно у одного из этих двух игроков есть выигрышная стратегия здесь, это мы... Ну, можно посидеть, подумать, это на самом деле несложный факт про такую игру, да. Раз за конечное число шагов заканчивается и всегда и нету нигде ничьих, то это должно быть на самом деле очевидно. Окей. So, a general theory of games says that in this game, either the first player has a winning strategy or the second player has a winning strategy. And now we, the logicians, ask which of the two players has a winning strategy. The answer is the following. The second player has a winning strategy in this game if and only if these two structures satisfy the same first order sentences. They are elementarily equivalent. When we prove this, try to prove this theorem, we will need to consider formulas of some complexity. They have some number of quantifiers, but not the number of quantifiers, but the depth of quantifiers. One quantifier inside another quantifier inside another, and so on. So we will need the following notion, the quantifier rank of some formula. It is applicable to any formula, not only to closed formulas. A quantifier rank of this formula, it is called atomic formula, is 0. It doesn't have quantifiers. Quantifier rank of negation is the same as for A. For conjunction, disjunction, implication, we take simply maximum. And finally, if we take a formula that starts with quantifier, then we add 1. With quantifier for all or with quantifier exist, then we add 1. For example, this is a formula. Can you calculate what is the quantifier rank of this formula? What is the depth of quantifiers? One quantifier inside another quantifier, and so on.
Well, the quantifier rank, it seems that's 3. Well, the premise of this implication and the first conjunct. If we see that there's 3.
Yeah, so here we have 2 quantifiers, and here we have quantifier exist. Inside it, we have conjunction. So we take maximum. Here we have 0, and here we have 2. So maximum of 0 and 2 is 2, and we simply add 1. So 3. Of course, we can define elementary equivalence, but only for sentences with quantifier depth at most n. So equivalence and equivalence means that for any formula, any closed formula, any sentence of quantifier at most n, they are the same. Either both true or both are false. So this was our first theorem. The second, so we will now relate this new equivalence and equivalence with games. We need a game. This is easy. Game with index n is played as follows. We don't need to, the first player doesn't need to choose any number. The number is already given. We simply start n rounds, and then, like here, we define who is the winner. So the game n simply is played n rounds, and then we see which player is the winner. And again, we can think which of the two players has the winning strategy in this game with number n, with subscript n. And the theorem says that these two models are elementary equivalent, elementary n equivalent, if and only if the second player has a winning strategy in this game number n. In fact, this first theorem easily follows from the second theorem, because two models are equivalent if and only if for every n they are n equivalent. For every n, they are equivalent for sentences of quantifier rank at most n, because every formula has some quantifier rank, so it is in some quantifier rank n. So this statement is equivalent to, for all n, this statement. Now let us consider these right-hand sides of the theorem. The second player has a winning strategy in this infinite, in this game with no subscript, if and only if for every n it has a winning strategy in this game. Ну вот, давайте, интуитивно. Почему в первой игре, вот без индекса, второй игрок выигрывал в исходной игре, выигрывал, тогда это тогда, когда он выигрывает во всех вот этих играх с индексом n. Ну, выигрывает, имеется в виду, имеет выигрышную стратегию. А что значит выигрышную стратегию? Он знает, как играть, что как бы ни играл первый игрок, второй всегда придет к выигрышу. А вот как бы ни играл первый игрок, а что, собственно, первый игрок делает в этой игре в самом начале?
Он выбирает число.
Да, вот именно первый, да, именно первый выбирает. Вот, собственно, здесь переход, что P имеет выигрышную стратегию здесь, только тогда, когда для любого n он имеет выигрышную стратегию здесь. Именно для любого n, потому что первый будет выбирать число, и вот при любом выборе первым какого-нибудь натурального числа второй игрок обязан иметь, ну, сказать, выигрышную стратегию, дальше знать, как играть, чтобы выиграть. А дальше гейм, собственно, продолжение той игры, это просто гейм n, если первый выбрал число n. Поэтому, ну, простое рассуждение.